thank you to the organizers. I'm really happy to be here. So you can see from the title what I'd like to talk about today. So a new paradigm for mathematical proof. Please note the question mark. But before we get into that, I want to start talking about some recent discoveries in mathematics because I don't think we do that in public quite enough. So there are two discoveries I want to talk about specifically, but I need to give a little bit of a prehistory first. And the prehistory comes from the 1990s, which was a great decade for solving really old problems. So Fermat's last theorem was mentioned in the previous talk, but another problem that fell in the 1990s is something called the Kepler conjecture. So this is about the most efficient way to pack three-dimensional balls in three-dimensional space. There's sort of an intuitively efficient packing that you've probably seen if you've been to a grocery store. This involves positioning the balls, the centers of the balls at these regular intervals on something called the face-centered cubic lattice. In fact, there's a second equally efficient packing, the hexagonal centric lattice. Already in the 19th century, Gauss proved that among sort of lattice-based packings, so sort of regular interval packings of the spheres, this was the most efficient, meaning the most dense by volume. But there's always the possibility that there's some irregular packing where you just sort of shove in the balls in an irregular configuration that's even more efficient. And that problem was very resistant to proof until 1998. So Thomas Hales reduced this to a sort of what's been described as a proof by exhaustion, so a very large number of cases that then are quite computationally intensive, but could be reduced to linear programming problems that he then solved. So this was a huge achievement. Big news was published in the Annals of Mathematics. Though sort of funnily, the referees put a little bit of an asterisk on the proof, sort of saying that they were 99% sure that the logic was correct, but weren't quite confident about all the computer calculations. You can think about how this might fit into the paradigms discussed in the previous talk. So what I want to actually talk about is the analogous problem in higher dimensions. So it's equally reasonable to ask about a ball in dimension 4, dimension 5, or dimension 6, and how what is the most efficient way to pack such things into n-dimensional space. This problem, I think, is wide open, and I would argue that mathematicians don't actually know whether it's sort of what to expect to be true, in particular, whether these lattice packings are still the most efficient ones. But there were a couple dimensions where there was a suspicion that the sort of regular lattice packings were the most efficient, and one of them is dimension 8, where there's an extraordinary object called the E8 lattice. And in 2016, in sort of a big surprise, it was proven by Marina Wyazowska that, in fact, this lattice packing is the most efficient, both among lattices and among irregular packings. Her proof, which is actually quite a short paper for mathematics, so 35 pages, something like this, involved a sort of connection, a surprising connection. She's really an expert in something called modular forms, which I think about as being something that connects complex analysis with number theory, but has these implications for discrete geometry that were sort of worked out about 13 years before her solution to this problem. But she was the one who came up with the clever modular form that solved it. Another remarkable thing about this story is because her proof was actually easy to digest for experts in the area, within a week they were able to solve another case, the case of the 24-dimensional balls in 24-dimensional space. And these are the only results actually still known, so dimensions 1, 2, 3, 8, and 24. Okay, so that's one example of a pretty exciting new development in mathematics, but I wanted to describe another one that's of somewhat of a different flavor. So Tim Gowers, in a different essay from the one that was just mentioned, reasons about two different cultures of mathematics. He's alluding to mathematicians who regard their central aim as being to solve problems versus those who are more concerned with building and understanding theories. I'm a little more on the theory side myself, so I wanted to sort of represent that point of view. And one of the big mathematical theories that's under study today is something called the Langlands program, and this is a sort of grand vision for a bridge between representation theory and number theory and algebraic geometry. One of the recent developments is a paper, Geometrization and Local Langlands, correspondence by Fargs and Scholze. It was posted as a preprint in 2021, and I think will be published this year. I think it's been accepted. But so this paper is, again, quite long, 356 pages. This is not normal for us, but there's sort of a lot of theory that went into proving the theorems that are stated in this paper. And in particular, Some of the ideas are sort of a new framework within to study objects that have both an algebraic and a topological framework. And that's actually not even in here at all, but in a bunch of supporting lectures. So this new theory goes by the name condensed mathematics, and it's been developed by Clausen and Schulze over a series of lecture courses for which there are lecture notes that are widely studied. We had a reading course on this studying here at Johns Hopkins. I think that's interesting about this is it's not really clear what the optimal method of dissemination for new sort of theory building within mathematics. So these lecture notes are not published, and I don't know if there's any effort intended to publish them. When you're developing something that's, as Grothendieck would say, sort of the rising sea, sort of developing a new framework within which to think about mathematical ideas, there's not always a sort of clear endpoint, a sort of clear cutoff, like this would be the publication. And if it all sort of depends on everything else, it's also sort of longer than the traditional journal model. Okay, so a recent development of a different sort, which I might describe as a human-computer mathematical interaction. This is an anecdote that took place in December. I was teaching a computational linear algebra course, and I prepared a practice final exam for my students. And I found out later from one of my TAs that one of my students asked one of the questions on my exam to Google. You might have observed that if you ask Google a question these days, it'll just attempt to answer it. So this is the Gemini large language model within Google. So the question is, does the set of orthogonal matrices define a subspace of the vector space of all square matrices? And Gemini said yes and gave an explanation. So I want to think about this a little bit more. So let me first explain what this is about. So matrices are just arrays of numbers, in this case, real numbers. So in a 2x2 square matrix, that just means you have 4 numbers, A, B, C, and D, arranged in an array. And the question is about orthogonal matrices, which are special matrices where the numbers have this particular pattern. Either they're S minus T, TS, or ST, T minus S, where S and T are 2 real numbers. There's a geometric explanation for all of this that we don't need to get into. So to say that the 2x2 matrices form a vector space just means that if you have a pair of these 2x2 matrices, you can add the coordinates and get another 2x2 matrix, or you can multiply each of the numbers in the matrix by a fixed real number and get another matrix, and these operations have some nice properties. And so what I was asking my students is that if you take the sum or scalar multiple of orthogonal matrices, do you get an orthogonal matrix again? This is really sort of a vocabulary question. The answer is sort of straightforward if you understand what any of these terms mean. So what does Gemini have to say about this? So Gemini answers yes and gives the following explanation. So the first thing, and these are all direct quotes from the screenshot I showed you earlier. It says, if you add 2 orthogonal matrices, the resulting matrix will also be orthogonal, satisfying the closure property for addition in a subspace. This is just wrong. So in fact, almost never if you add orthogonal matrices will the results be orthogonal. The second thing it said is multiplying an orthogonal matrix by a scalar preserves the orthogonality condition, meaning the set is closed under scalar multiplication. Again, this is wrong. So if you multiply by plus or minus 1, then it's still an orthogonal matrix. Otherwise, it's just not. And then the final is the zero matrix is considered an orthogonal matrix, including the zero vector is included in the set. So this is something you need to check, but the zero matrix is not an orthogonal matrix, so this is also completely wrong. So of course, then my student was confused, and then my TA was confused, and so on. So despite the fact, I won't show the screenshot again, but Gemini gave correct definitions of subspace, correct definitions of orthogonal matrix, so was referring to the correct terms, but every single logical assertion in this is basically incorrect. So the screenshot I just showed you was from February, and the models have gotten better since then, but I think the point still remains. So this is a question I asked the Gemini 2.5 Pro reasoning model, which is the top model available from Google at the moment. And it's about my particular subject area. So the question refers to something called a category, which is a technical term in mathematics introduced in the 1940s by Eilenberg and MacLean. I'm referring to categories as one-dimensional categories because there's a new infinite dimensional analog, something called an infinity category. And there's a close analogy between infinity categories and one categories. And a lot of theorems that are true for one categories extend for infinity categories, and the proofs are similar, more or less the same. So what I asked Gemini is it true that in infinity categories, idempotent complete clarifying, in the infinity categorical sense, if and only if its homotopy category is idempotent complete in the one categorical sense. And what it gave me, it's much longer than I displayed here, but I have the screenshots if anyone wants receipts, is clearly written argument that's mostly correct, but there was a very subtle error. And it's a sort of kind of optimistic error that human mathematicians will often make that assume that the sort of infinite dimensional and the one dimensional, it's sort of basically the same, and the coherence issues sort of work out. And because of that subtle error, even though if I went through line by line, in this case, most of the statements were correct, the conclusion, I asked the yes or no question, is wrong. It's completely incorrect. Basically, everything in this concluding paragraph I show on the left is wrong. I tried to help Gemini by correcting the point of the error, so it was using an incoherent definition of an idempotent rather than a coherent one. It acknowledges you're right to press on subtleties of coherence and infinity categories, and then acknowledges that there is a more coherent definition than the one that it used, and then gives an argument that that doesn't matter, and that again is wrong. So this is completely incorrect. Okay, so I'm calling this vibe proving. You might have heard of vibe coding, which, as I understand it, is an opportunity that people who have no training in computer science might nevertheless be able to write a computer program. What I'm concerned about is that, it's sort of one thing for me to make fun of Gemini for messing up something in my particular subject area, but what I'm worried about is somebody coming along and sort of vibe proving results in infinity categories with the assistance of a large language model, and what they'll get, looks pretty good, but could be totally wrong. And I would say a lot of the mathematical text generated by top reasoning models today is pretty good, and all of it looks good. It's beautifully written in LaTeX, among other things. There's a caveat that if there are any numbers, then it's totally wrong. It cannot do arithmetic. I mean, there's reasons why large language models would never be able to do arithmetic. It's just the wrong architecture for that. But pretty good is not good enough. So one minor error could make an entire logical argument reach the wrong conclusion, true instead of false. So if Simon drew the box of sort of the AI within this kind of Gödel mathematical universe, I would put it outside the Gödel universe, because the problem is, some of it is just not true. And this is something that I'm particularly concerned about, as a practitioner, and I said maybe also as an editor of journals. So I work in a subfield where papers already tend to be quite long, technical, difficult to referee, and I'm extremely concerned about AI-generated mathematical proofs. Already, I think the amount of expertise that is needed already to sort of vet these very subtle, very long arguments, finding somebody with the right expertise to referee a paper is already sort of difficult enough. And I guess I'm just worried about sort of the floodgates, maybe the volume as much as any other things. And this is actually sort of an interesting question, is sort of why has peer review worked at all over the years? Why is mathematics largely avoided the replication crisis that has confronted some other fields? And what peer review means in theory is, careful refereeing should lead to error-free publications. So, we make a clear distinction between sort of preprints and the published literature. But, as experience shows, the mathematical literature contains plenty of mistakes, famous ones, small ones, is not always corrected. There are some errata, but there are sort of mistakes that the experts in the fields will know that this paper is unreliable, and the students in the fields won't necessarily know that. That can be a problem. But how it works in practice, I think, is a little bit different from how it works in theory. So in theory, any proof should be reproducible by any reader, or maybe I should say any reader with a sufficient background to be the audience for the particular paper. And what a proof is something that allows a reader to understand for themselves why a result is true. I was particularly interested in Jennifer Nagel's points this morning about sort of shared consciousness and how shared understanding would work in the mathematical realm. One thing that's remarkable about the mathematical community is the wide degree of consensus. People all around the world who I've never met, and I have a very similar worldview about a whole bunch of different things. And it's interesting to think about how that sort of common understanding has been developed. I mean, on the one hand, an extremely efficient way to communicate mathematics is one-on-one through an in-person communication. Certainly my preferred mode, but I was teasing one of my collaborators the other day that, here's how we actually talk to each other in practice. So my collaborator will start to say something, and then as soon as I get sort of the gist, I completely tune him out, and I come up with the argument for myself. Then when I think I've understood it, I want to make sure I've understood the correct thing, so I'll describe it back to him, and as soon as he gets the gist, he completes me, tunes me out, and then somehow this is the sort of most efficient way for us to have a shared mathematical idea is we communicate kind of just, and this is somebody with whom I communicate extremely well. This was meant to be a model of highly efficient communication. So there's something sort of shared and in community, but also kind of solipsistic in that you're constructing the proof really in your own head. And that's the sort of only way that mathematical understanding happens, at least in my experience. But back to peer review. If there's a mistake in a paper, I think what happens more often than not is that the authors are the one to catch it. But when it's not the authors, what happens is a grad student will come on a few years later, somebody who's trying to really become an expert in the particular field, and they'll read it extremely closely, line by line. They'll get to something that they don't quite believe. They'll ask questions, and that's sort of how mistakes are caught. So as long as there are enough readers of the literature that we're writing, mistakes are eventually caught. And another important component here is there's this sort of phrase, garbage in, garbage out. So when mathematicians share their work, the first thing they'll do is they'll take an article and post it to something called the archive. That's ARXIV. It's a free online preprint server. There's a little tiny bit of moderation, but basically you can post whatever you want on the archive. But mathematicians hold themselves to quite a high standard before saying that something is ready, that is archive worthy, even though it's just a preprint server, even though there's no peer review. I won't post anything to the archive unless it's ready to be submitted to the journal, unless I really stand behind it. And I think it's because, mathematicians are investing that much care and carefulness in their initial claims that the literature is sort of as reliable as it is. Okay, but sometimes all of this breaks down, and the experience of being completely wrong in mathematics, even in published mathematics, is very universal. So I thought I would pick on some Fields medalists. So one Fields medalist, Vladimir Voivodsky, had the experience of finding some mistakes in some famous papers of his. One I think he caught when he was giving a course about his Fields medal work a few years later. Another was a result in a paper of his clearly contradicted a result in another paper, and it took about 13 years after that to figure out who was wrong and who was right. And this sort of distressed him, the sort of amount of time within within a mathematical lifespan. This is a blink of the eye before these mistakes are caught, but within a human lifespan, he was sort of distressed by this and wrote that a technical argument by a trusted author, which is hard to check and looks similar to arguments known to be correct, is hardly ever checked in detail. So another Fields medalist, this is a more recent story, Peter Scholze, who was of the condensed mathematics earlier, had a particular proof in this condensed mathematical framework that he discovered but also sort of doubted. And even though this is being widely studied, there are forces reading it on the world, he wasn't sure that anybody else was going to check his proof. And he described it this way. So while I was very happy to see many study groups on condensed mathematics throughout the world, to my knowledge, all of them have stopped short of this proof. And yes, this proof is not much fun. And in particular, this is new mathematics, and he wanted to build further theory on top of it. And his concern is if this proof is wrong, then everything I'm going to do now is going to collapse. So it's a real sort of moment of crisis, sort of at the research frontiers of mathematics. Okay, so all of that was meant to describe a problem, and now I want to propose a potential solution. This is the new paradigm for mathematical proof with a question mark from the title. And what I've shown you here is my most recent contribution to the literature that's technical and kind of too long and hard to referee. So this is a paper with 4 co-authors that we posted to the archive last summer. It's contains some results that we announced in 2019, so 5 years before we submitted the paper and or completed the paper. Of course, part of the story is you're busy and other things interfere, but also the proofs were sort of harder to pin down than we thought. There were some subtle details that came up in the write-up that we didn't anticipate when we thought we had proven the theorem in 2019. And what I've highlighted here, even though I know it's illegible, is this funny box around this phrase, formalization. So there's 75 pages of pen and paper mathematics, and then an appendix that refers to something a little bit strange. And what it's referring to is a piece of software called a computer proof assistant, sometimes also an interactive theorem prover. And this is a software that can certify the correctness of a mathematical proof that has been written in a precise formal language. So the typical mode of using this software is that a proof is written laboriously by a human or maybe a computer scientist. This is a process called formalization. So typing the proof sort of line by line into this piece of software called a computer proof assistant. But in principle, of course, a generative AI could do the typing. So a generating AI, some black box that we don't trust at all, could be trained to output its text in the syntax of a computer proof assistant. Then this architecture that is written by humans, this trusted piece of software, could verify the logic of the argument, even if we are not inclined to trust the AI. That's called auto-formalization. And so what our paper contains is an appendix that describes an accompanying library of formalized proofs in a computer proof assistant called AGDA. So this library is hosted on GitHub. This is sort of the README from the GitHub. And the main definition, which the paper was about, is an equivariant, I kind of forget the title, equivariant Cartesian cubical model of type theory. This definition just takes a few lines to encode. Of course, this is completely impenetrable. So this is an artifact that is submitted alongside the paper. The paper, of course, is actually still awaiting a referee report. This timeline is actually quite normal for us these days. So I want to describe this process, this idea of computer formalization in a little bit more detail. So it's a new, not yet widely practiced method of developing and communicating mathematical proofs interactively through the use of a computer program called a computer proof assistant. So this interaction is between a human and a computer, a human user of the proof assistant and a computer. So what the mathematician does is they input each line of their proof in a precise syntax. So you have to have all your commas in exactly the right place, the spaces, the indentations, the capitalization, everything. The computer then checks that the logical argument supplied by the user produces a valid deduction of the claimed mathematical statement. So the computer is programmed to know a formal logical deductive system, and in the communication process, the user is explaining which logical rules I'm applying to which hypotheses to reach which conclusion, and then the computer is checking that that indeed does follow according to the rules of the logical system. And depending on the sophistication of the program, it might also assist the mathematician in certain ways. So all computer proof assistants do real-time checking, so catching errors of reasoning, which could be an unjustified assumption, a missing case, and so on. It can also communicate the current state of a complicated logical argument. So, students who are learning proofs will often sort of get lost in the middle, and they'll forget that they're arguing by contradiction, or they'll forget that something or other is the goal and not a hypothesis. But the computer can communicate that information in real time, which I think has some interesting implications for pedagogy. And even it could suggest or automatically generate some proofs. So auto-formalization right now is sort of in its infancy, but it's something we're all expecting to improve. I think the real sort of surprise about this is again, sort of this level of instantaneous real-time feedback. So an aside that I don't have time to discuss here is that modern proof assistants often use a newer formal system, something called dependent type theory, in place of Zermelo-Fraenkel set theory and first-order logic. I'd be very happy to talk about that offline. So this new paradigm, computer formalization, in fact, was turned to by both of the authors that I mentioned previously. So Voevodsky in the mid-aughts stopped doing pen and paper mathematics entirely and spent the last decade of his career developing a new formal system. So it's an extension of the dependent type theory that I just mentioned that makes it easy for him to reason formally about the sort of higher structures, the particular area of mathematics that he was interested in. And then he did all of his mathematics in the computer proof assistant ROC. The quote I read to you from Peter Scholze was actually on a blog post challenging the formalization community to use a computer proof assistant to verify the theorem that he doubted. And the lean theorem prover community took that challenge on and launched this collaborative effort, sort of inspired, I guess, by Scholze's stature in the field to attack it. So what you see on the right is a dependency graph from a blueprint that was created collaboratively with Scholze, so where he gave a very detailed outline of the proof, the sort of statement that he was most concerned about, and then the things that it depended on, and then the definitions that those depended on, and the theorems those depended on to make those definitions make sense, and so on and so forth, and broke this down into a problem that could be attacked by many people at once. And this is because all these circles are filled in green, this shows that this has all been completed and verified by the proof assistant lean. So there's no doubt anymore about that theorem, and of course the understanding of it improved through this process as well. So I mentioned, Hale's solution to the Kepler conjecture. I think he was a bit annoyed about the asterisk, because, happy his papers in the annals, unhappy the referees didn't quite certify it correct. And so he launched a multi-year project to formally verify this, and a computer proof assistant, Isabel and Hall Light, took 11 years and resulted in another sort of very long paper with 22 authors. Fermat's last theorem is actually in the process of being formalized right now. So I very much agree with Jeremy's perspective that there's a lot of information in this proof, and the motive. So there's a couple different motivations for formalizing Fermat's last theorem. I mean, one is maybe this question: is there any one person who completely understands the proof of Fermat's last theorem? So sorry, this is the statement that there are no integer solutions to x to the n plus y to the n equals z to the n among positive integers when n is greater than 2. Really, Kevin is interested in all the mathematics that is going to be developed along the way to formalizing this. So there's a lot of very interesting theory that was developed in pursuit of that problem that is, sort of absolutely vital to number theory today. And he's interested in having that theory formalized. And this is kind of the headline result that gets you the funding. So the moral of this is that proofs at the frontiers of mathematics, extremely long, extremely complicated, extremely technical proofs, are formalizable, but only with monumental human effort via large-scale collaborations. I'm personally interested in the question of what's formalizable sort of on the cheap, meaning with fewer human resources. And an interesting case study there is actually the Fields Medal work of Marina Vyazovska that I mentioned at the beginning. So the E8 lattice is the most efficient hacking for spheres in 8 dimensions, is in the process of being formalized by her and a master's student. And if they're successful on a smaller team, I'd be very interested in that. Okay, so to wrap things up, I want to say a little bit about the personal experience of using a proof assistant. So when you're explaining a mathematical proof to a computer, it requires sort of absolute precision, in particular regarding the exact definitions of mathematical terms. And when I talk about mathematics with a non-mathematician, one of the things that I emphasize is the reason that we have such a high degree of consensus in the field is that we're very precise about definitions. So we don't sort of argue what a group means. But on the other hand, there's sort of famously like 20-ish logically equivalent definitions of a group. And to a human mathematician, you can translate back and forth between them very quickly. But to a computer, not at all. You have to explain exactly which perspective on groups you're taking at each line in the argument. This can be deeply frustrating, but also requires a sort of flow state of very, very deep focus. So in my experience in trying to formalize something, if you're not thinking perfectly clearly, if you don't have the ideas sort of and the real reason why something is true extremely clear in your head, there's no point in trying to type anything at all because the computer will reject it immediately. And so somehow, paradoxically, the fact that I'm required to be much more precise helps me focus much longer. And because you're getting feedback in real time from the proof assistant, this also activates reward mechanisms, in contrast to sort of a typical day where I start in the morning and thinking I've understood something very well, and by the evening I've made negative progress and realize I didn't in fact understand the thing that I thought I proved yesterday. When a proof assistant accepts something, it feels great. And sometimes this has been described as a sort of gamification of mathematical research. It'll be interesting to see sort of if and how this changes the process of proof writing. But on the other hand, there's more to mathematics than rigor and proof. So this is the title of a famous blog post by Terry Tao. Mathematicians also like to talk about analogy, the art of giving the same name to different things. And so formalization, this enforcement of ever greater rigor, kind of runs counter to this particular vision of mathematics. So Terry Tao distinguishes between kind of a pre-rigorous stage, a rigorous stage when you learn to reason formally, and a post-rigorous stage, which for him is really an ideal, where a mathematician who has been trained on sort of formal proof now has the right intuition to reason informally, to daydream, and nevertheless have things that maybe they don't know how to make formal, but are somehow deep, true in a kind of deep sense, maybe in sort of the sense that has been alluded to earlier today. Okay, so I'm presenting computer formalization as sort of an interesting new paradigm for mathematical proof, but I wanted to make it very clear that I don't think there is consensus about this within the mathematical community at all. In fact, I'd say that this is a very much minority point of view. So I'd estimate that most departments contain few, if any, mathematicians who are currently working with proof assistants. So for instance, my department contains one. And even early adopters would argue that this is sort of too hard to be practical for most kind of day-to-day proof writing. And also whether the mathematics you're trying to do is formalizable depends very much on the subfield you're in. And it's interesting to think about what potential solutions to that problem will be. I'm particularly interested in sort of domain-specific foundations. And of course, the whole point of this is to help humans understand mathematics. And I could see sort of advantages to this new paradigm, but it would also be a real shift. But finally, part of the motivation for this was talking about AI, and as a defense of the mathematical literature against vibe proving or sort of AI-generated literature. So I am not willing to kind of stand behind computer formalization as a new paradigm for proof writing on behalf of the human mathematical community, because I don't think I speak for the human mathematical community, but I am willing to make a stronger stand here. So despite the well-known imperfections, the mathematical community can take deep pride in our overwhelmingly reliable and continually improving standards for mathematical proof, where things get sort of more precise and clearer over time. And I think we need to demand the same for AI in the mathematical realm. Technology companies are interested in being able to claim that they can do mathematics, but I think it should be up to human mathematicians to decide whether an AI is doing mathematics or not. And in particular, by sort of maintaining high standards, I think we'll be a little bit of the naysayers, the sort of stick in the mud saying, this is not good enough. This induction is not needed in this proof, something like that. But I think it could be beneficial for overall reliability in the long run in pure mathematics, which is, of course, what primarily motivates and interests me, but also other domains, which perhaps have real-world applications that are mathematizable. And then specifically, I want to propose the following norm for the mathematical community when it comes to original mathematics produced by an AI system, which is that it will not be considered as a proof unless it has been formalized. And specifically because it's about communication and not just truth, what I think what we should demand somebody who's developing a model for mathematics to produce is paired text with a natural language proof, a summary written for human mathematicians, and proof in the syntax of a computer proof assistant that can be verified by the computer proof assistant, though there will still be some human refereeing in the loop to check that the statements that have been proven by the proof assistant correspond to the statements on paper. That's all I wanted to say. Thank you very much.
Let me just say thank you again so much to Sean and Janan and everybody who's helped organize this. This is amazing. This is an amazing event. And thank you so much to Emily for that super interesting talk. And the issue is so relevant and live. It's just coincidental that I just finished co-teaching a course with a colleague in the math department, Michael Harris, who works in the Langlands program, and a large chunk of it concerned exactly this issue. And we had Kevin Buzzard in, and he talked about how it felt like gaming to work on this Fermat's last theorem because you always get the ding, and so it was very interesting to get different perspectives on where things might be going. The opinions vary dramatically from in 10 years, mathematicians will be out of business to this is going to have zero effect at all. So I have no idea, and I'm not going to make any predictions. That won't be my talk today or my comments today. I'd rather try to situate and I guess you could say complicate Emily's talk in a more long-standing debate about the nature of proof, which has really been central to Western philosophy. The first extended discussion of proof in the West is Plato's Dialogues, and I just want to remind everybody what a strange thing that was, right? So there was advanced math all over the globe. The Mesopotamians were doing recreational math in 2000 BC. Yeah, I mean, like exercises in the back of the book or on the back of the cuneiform tablet, I guess. But they didn't have proof. They had like manuals with algorithms and explanations for why the algorithms worked. And the kinds of problems they were concerned with were practical problems of agriculture or commerce or whatever. It was only with Plato's dialogues, like starting with the Meno, like the Meno is a classic example of the discussion with the slave boy, where you first of all have like pure math, for lack. I mean, it's not. There's no practical suggestion involved, and there's a demand for proof. They don't. The idea isn't just tell me the answer and give me a method, But I want to know something. In the case of the Mino, it's you start with a square, and now how do you make a square of exactly twice that size? And the slave boys walked through the fact that, well, you would have to take the diagonal as the sides of the square, and you can see why that would be so. But in the particular case, the diagonal is an irrational length, and so that wasn't a number by the Greek standards, and so it was the point is that this is a whole new approach to mathematical inquiry, this proof based argument, and Euclid's Elements is like 100 years after that. So anyway, so so around that time you got proof enter the scene in the West, but you also have the introduction of Aristotle's formal logic. And one of the really strange things about this combination of developments is that Aristotle's formal logic, the syllogistic logic, you could never do any math using that logic. So for about 1500, 1700 years, you've got this very weird situation where, Kant tells us that Aristotle settled logic, right? So basically until Kant, you've got the laws of logic, and it's Aristotle with some bells and whistles. But then you've got this other thing called proof and math, and it has nothing to do with Aristotelian logic. So it was only with the development of Frege's and Russell's logic, one of their motives was to come up with a logic that could do justice to the reasoning in math, that you had an overlap between a potential overlap between the kind of reasoning that mathematicians actually use and the thing that philosophers had been focused on for 2,000 years called logic. Okay, so in thinking about that tradition, historians have drawn a distinction then between two notions of proof. And unsurprisingly, one of them is called platonic proof, corresponding to the kind of argument that you find in the Meno or then in the Elements. Other characters that are supposed to be in this lineage include Descartes. And then the other is Aristotelian proof. Leibniz is another example, and then certainly Frege and Russell would be examples of this. And the idea of a Platonic proof is that a Platonic proof is the kind of thing that tells you, just like was said in another talk, why the thing has to be true. It's the kind of proof one desires. It resolves the mystery. It's like, aha. It's that kind of moment, but it's not rigorous. It's usually, it involves gesticulations and, drawings, and what will cause you to have the aha will depend a lot on you and your background and all these things. A formal proof, by contrast, today, after the invention of Turing machines and so forth, we can cash out a little more carefully what's so great about formal proofs. Formal proofs have the feature that you and I don't have to agree at all on what the words mean. We don't have to agree at all on what the world is like. We just have to agree on whether the following sequence of symbols, every line is either an axiom or follows from the previous line by a rule of formal inference, the last line of which is the shape of the claim to be proved. And we could then feed it to a computer, and the computer would say yes or no, and it's a perfectly objective fact, it seems like, whether that thing is a proof, and you and I can have whatever views we want to have about the nature of math or what numbers are or whatever. So they're two quite different pictures of proof. Okay, so the question arises, what, if anything, is the connection between these two? Now that we have a logic that's potentially adequate for math, what's the connection between the two? And to the extent that the question has been explicitly answered, the implicit or the explicit answer has been, the connection is the following. At the very least, a alleged proof, like something you'd publish in the Annals of Math, an alleged proof in ordinary language with symbols for human consumption is only a real proof if there exists a surrogate in the language of it's traditionally been first order ZFC for the nerds in the room, the small large cardinals, but the details don't matter. But first order ZFC, where the final line is a translation of the claim to be proved in that language. Whether the other direction is true is more controversial, but the only if claim is hard to deny. I should say though that has made some people uneasy, and the my co-instructor Michael likes to dub this. You can sort of infer maybe how he feels about this. The central dogma of mathematical formalism is what he calls this. Now he's considering an if and only if claim, and as I say, the only if it seems dubious for reasons that are on your handout in the last paragraph, which I think I'm going to skip for time. But let me explain to you why that generally accepted, I think, to the extent that people think about these things, that generally accepted view is defensible. Let me just try to defend it quickly, and I think Emily agrees with. I mean, yeah, she clearly agrees by the nature, but given her conclusion or the norm she suggests. Okay, so why would you think that Aristotelian proof, or that is proof in first order logic from the ZFC axioms with the small large cardinals, blah, 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 is the final arbiter for normal proof in the everyday sense of mathematicians proving theorems? Why would you think that? Well, here's an argument that I think pretty much settles the question. So a major development in the 20th century in mathematical logic was the discovery of independence results in set theory. So people have already mentioned independence in arithmetic, specifically Gödelian independence, and something that's peculiar about those cases is on the general account, the truth value. You're just learning the limitations of a formal system. So in the case of piano arithmetic, you're not really skeptical that arithmetic's consistent just because if it is, you can't prove it from it. It's just you're learning that if arithmetic's consistent, it's got this limitation. It can't prove that it's consistent. Okay, so that's just a thing. But there's another kind of independence that was discovered in set theory, which, as I say, is commonly thought to be the foundation of math, but not universally. That where fundamental questions of that subject are not just independent, but the proofs that they're independent do nothing to tell you whether they're true or false. So the very first question on Hilbert's list of famous questions at the turn of the 20th century was the first question you ask when you realize there are different sizes of infinity, which was what George Cantor discovered, or according to the standard line, which is that give me a set, can be finite or infinite. If I take then the set of all subsets of that set, it will have greater cardinality. How much greater? First question you ask. Like, is it the next greatest in size? If we assume the axiom of choice, it's got to lie somewhere on the hierarchy of sizes. So is it the next greatest in size? Is it way? Turns out, thanks to theorems of Gödel, Cohen, and then Easton, that you have just dramatic freedom as far as the axioms are concerned. You can consistently, if the axioms are consistent, just basically take whatever line you want on how big that operation is. And similarly for other power sets of other infinite sets. So this is just a very concrete question. I mean, the most concrete question you can ask about infinite sets, and the proof that you can't settle it tells you nothing about the answer. So okay, so the way that's written is like this on your handout. If ZFC is consistent, con ZFC, if con ZFC, then con ZFC plus CH. That is, if ZFC is consistent, then so is ZFC plus the continuum hypothesis. And similarly, if ZFC is consistent, so is ZFC plus the negation of the continuum hypothesis. Okay, here's the point that I want to make. All of that, in order to be done, has to concern formal proofs. There's no way you could make such an argument about informal proofs. There's nothing to work with. It's too messy. So you work with formal proofs. What that's saying is take the formal language of ZFC with one non-logical constant is a member of. If you can't get 0 equals 1 or anything, I mean, if the thing's inconsistent, you can get everything. So if there's anything it doesn't prove, then it doesn't prove in particular the continuum hypothesis in this super formal, written out way where the only non-logical constant is a member of. I mean, just to be clear, even writing the axioms of set theory in this formal sense are hard for a human being, let alone any proof. And similarly with the negation, that's what you prove. Okay, here's the point. That's a claim about formal proofs, Aristotelian proofs, Phrygian, Russellian proofs. Nobody's looking for the truth value of the continuum hypothesis anymore by proof. Some people have inaugurated a new project of looking for new axioms to supplement ZFC and large cardinals. But that's because the independence results show that you cannot prove the thing. But if that's the case, then informal proof is answering to formal proof, and formal proof is the final arbiter there. It's a necessary condition. Okay, so I'm going to skip, is it a sufficient condition? I think there's a good case to be made that certainly in the ordinary sense it's not. We want explanation, we want insight, and we don't want a phone book of computer code, even if it's been checked by a computer. But as Emily's pointing out, as far as for all we know, proofs will become increasingly synthetic. They will increasingly involve, on the one hand, a computer, and on the other hand, a person working in tandem, and you'll have a result that is their joint collaboration. So we need to update this necessary condition on proofs now that some of these proofs will be partly generated by computers. And Emily proposes, I think, plausibly, the following norm: to any artificially generated mathematical text should not be considered as a proof unless it's been communicated in both natural language text paired with a computer formalization of all definitions, theorems, and proofs, and the formalization has been accepted by the proof assistant, and the human expert referees have vetted both the formalization and the paired text. So I think that the best way to understand what Emily is doing here is not trying to analyze our concept of proof. I mean, part of the point is maybe that concept is sort of not up to the task now that things are changing, but advocating a policy position about how to proceed in the future. And this, I think, is exactly the right way to approach this issue. And I also think it's the right way to think about the central dogma, to return to that. So ask yourself, what kind of claim is the central dogma? The central dogma, to use Michael Harris's language, says that, again, a proof in the ordinary mathematical sense is valid if and only if, but let's just stick with the only if, there exists a formal surrogate of that proof that it somehow indicates the existence of, that's formally valid, like you could check it with a computer. What kind of claim is that? So one answer would be like, that's a factual claim. There's a pie in the sky answer to what's a proof. I think that the much more sensible view, I think it's hard to even make sense of what that could mean. I think the much more sensible view is this is the best policy to proceed by. We should be seeking proofs such that you could formalize them and then check their surrogates on a computer. Okay, I just want to finish with, I said I would complicate also. So Emily correctly, highlights this remarkable fact about math. I feel like people aren't puzzled enough by this fact, which is that in some sense, there's a remarkable amount of agreement in math. And why is that? And what exactly is agreed on? And so Emily, I think, rightly says that, part of the story is that mathematicians are good people. They concentrate, they carefully read the papers they're asked to referee. They're humble in claiming to have a proof. Agreed, completely agreed. But I actually think that she's on to a much deeper problem that we don't have a good answer to. And let me just try to dramatize it, and then I'll drop the mic. I'll leave it there, and you can answer it on your own. But let's take a very simple example that everybody's been exposed to, probably, like Euclid's theorem. There are infinitely many prime numbers, or if there's any finitists in the room, for any number m, there's an n that's prime, and n is greater than m. So what exactly, when somebody says everybody agrees to the proof of Euclid's theorem, what exactly is agreed to? So then, a first thought would be the theorem. But it's like, wait, that doesn't make a lot of sense. I mean, that's like this bold existential conjecture. Is it, do the mathematicians know something that the physicists don't, that along with the bosons and the fermions, there's also the prime numbers? That seems not like the most charitable way to understand what it is that's agreed to. So somebody says, oh, come on, you're being a philosopher. That's not what we agree to when we agree to Euclid's theorem. What we agree to is the logical truth that if And now things get complicated already. You have to insert a finite subset of the axioms because you can't have a well-formed sentence involving all the axioms, and there's infinitely many axioms of piano arithmetic in a first-order setting, but whatever, set those technicalities aside. If the axioms or a collection of them, then Euclid's theorem. Well, strictly speaking, what you would want to say is that's a validity. So it's a metalogical claim about the status of a conditional. So like, if snow is white, then snow is white. That's a logical truth. The claim that it's a logical truth is a metalogical truth that's not itself a logical truth. So, okay, it's a metalogical truth. Okay, so it's the metalogical claim that there are infinitely many prime numbers is provable from some axioms. Okay, roughly speaking, but that also doesn't seem like that could be what everyone agrees to. I mean, that suggests that everyone agrees to classical logic, and there's certainly disagreement about logic, just like there's disagreement about non-logical axioms. You know, I mean, just like there's disagreement over the axiom of choice, there's disagreement over the law of the excluded middle. So that doesn't seem right. So somebody says, oh, come on, you know what I mean. What I mean is the following. If the axioms and classical logic is right, then you can prove that there are infinitely many prime numbers. Or in other words, you can prove that there are infinitely many prime numbers from the axioms using classical logic. In other words, the hope is, can't we factor out what, like factor out all the things you could debate about and then just agree on this conditional claim that's the thing that everyone is really agreeing to? And that explains the consensus, because you don't have to take a stand on any controversial philosophy. And I just want to conclude by saying that, maybe there is an answer to the problem of why is there so much agreement in math. I don't know the answer, but it's not that. And the reason it's not that is because what follows from what, even in a logic, depends on the logic you use to check. So we already have to agree on logic in order to agree on what follows from what in a logic. So why do we do that? And same with our meta theory generally, the axioms of the non-logical axioms of the meta theory as well. So anyway, I just want to say that I think the problem of what explains agreement in math is like wide open and deep, and I'm glad that that Emily brought it up. I'll leave it there. Thanks.